Hello everyone. In this class, we are going to discuss in detail about the coherence because this chapter is all about interference and we know that without coherence, interference is not possible. In your plus 2 higher secondary classes, you already learned the basic definition of coherence. That is, suppose we have two waves and they are said to be coherent if they have same amplitude, same frequency, same frequency, and maintaining a constant phase difference between each other. So this constant phase difference is the important thing, important parameter we are going to discuss about. So coherence, the standard definition of coherence is the measure of correlation that exists between the phase of two waves. That is the standard definition of phase difference. So the phase difference between two waves is essential to maintain coherence. Okay. So there are two types of coherence. That is, there are two types of coherence. One is temporal coherence and the other one is spatial coherence. Okay. So we are going to discuss in detail about coherence, and we know that coherence means suppose we have two waves and it is said to be these two waves are said to be coherent. Suppose they are having the constant amplitude, same frequency, and maintaining the constant phase. And there are two types of coherence. One is the temporal coherence and the other one is the spatial. Okay. The first one which I am going to discuss about is the temporal. Okay. So in the temporal coherence, the type the first thing which we are going to discuss is about the temporal coherence. Okay. So the temporal coherence is actually a time dependent coherence. Okay. The temporal coherence is actually a time dependent coherence, and the temporal coherence is giving an idea about the spectral purity of the light. That is, suppose we have a light source, the temporal coherence is giving the idea about the spectral purity. So it is a measure of correlation with phase of a wave at two different points. Suppose we have a wave here. Okay, in this picture we have a wave, and I'm considering two different points. Okay, and at a particular time t, and I'm measuring the phase of a wave, and I got a value that is at this particular point I have phi a, and at this particular point I have phi t. Okay, so this particular point is at phi a, and this particular point is at phi b. Okay, and this is the along the propagation we are taking 2 points. That is, this is the propagation direction. So along the propagation we are considering 2 points A and B, and we are checking the phase. So at a particular time, I got the phase of the wave is phi A minus phi B. Okay, and the same wave and at a different time, that it is t dash, and again and I'm checking the phase and I got another value, the same point, and at different time I got the value of phase, that is phi dash a minus phi dash b. Okay, once again, at a particular time t, in a same wave, I'm considering 2 points which is along the direction of propagation, and at a particular time t, the phase is phi a minus phi b. At the same wave, the same points at a different time t dash, the phase is phi dash a minus phi dash b. Phi a minus phi b, which is equal to phi dash a minus phi dash b. If this phi a minus phi b is equal to phi dash a minus phi dash b, then we can say it is temporally coherent. Okay, this is the condition of temporal coherence. Once again, suppose I have a wave and I am considering two different points along the propagation of the waves. At a particular time t, I have the phase which is phi a minus phi b, and the same point, the same wave at a different time t dash, I have the phase which is phi dash a minus phi dash b. Okay, if this phi a minus phi b is equal to phi dash a minus phi dash b, then it is said to be temporally coherent. Also, there is two other parameters. Okay, I can discuss that after the spatial coherence. Another one is spatial coherence. Okay, so in this picture itself, you will get an idea. So we are taking two different waves. This is position dependent coherence. Spatial coherence is position dependent. Okay, so the spatial coherence is a measure of correlation between phase of a wave at the previous case. In the case of temporal coherence, I took 2 points which is along the direction that is parallel to each other. But in the case of spatial coherence, and I have a point A here and I have a point B here, and I have two different waves over here. Okay? And again at a time t, I'm checking the phase, and I got which is equal to phi a minus phi b. Okay, that is at a particular time t. I got the value of phase is phi a minus phi b. And at a time t dash, again I'm checking the same points, but in a different time I'm checking. So I got another value that is phi dash a minus phi dash b. Again, according to the spatial coherence, if that is phi a minus phi b equal to phi dash a minus phi dash b, then it is said to be spatially coherent. Okay, that is, if or we can say that the spatial coherence is the correlation between the phase of a wave at different points perpendicular to the direction of propagation. In the case of temporal coherence, we took two different points which is parallel or along the direction of propagation. In this case, we are taking 2 points which is perpendicular to the direction of propagation, and we are checking whether they are maintaining a constant phase. Okay. In both the case of temporal coherence, it has a constant phase difference along the direction of propagation, and in the case of a spatial coherence, it has a constant phase difference perpendicular to the direction of propagation. Okay. So in the previous case, the case of temporal coherence, we had two different points which is having a constant phase difference along. Okay, this is very important. Along the direction of propagation. Okay, so that is a spatial coherence. And now, in the case of coherence, we have two other parameters. One is coherence length. Okay, one is coherence length, which is represented as L suffix C, and the other one is coherence time. Okay, one is coherence length, which is L suffix C, and the other one is coherence time. Okay, so the coherence length is the average length that two waves or the two particular different points are maintaining constant phase. Okay, this is the average length because it is impossible to maintain an infinite phase relationship. So in a particular period of time, it will be maintaining a constant phase relationship. So the coherence length is the average length of a continuous wave thread which is having a phase relationship. Okay, so the coherence length is equal to lambda square divided by d lambda. That is, suppose we have two wavelengths, or suppose an ordinary source of light is emitting particular wavelength, and this lambda square divided by, that is the square of wavelength divided by change in the wavelength. Coherence length is lambda square divided by d lambda. And another one is coherence time. Okay, that is the time over which the phase relationship is revealed. This is the average length. Here, this is the time over which the phase relationship is maintained. Okay, so coherence time is the time over which the phase relationship is maintaining, which is equal to Pc is equal to Lc divided by C, where Lc is the coherence length, C is the velocity of light in factor. Okay, once again, there are two parameters which is related to coherence. One is coherence length and the other one is coherence time. Coherence length is the average length at which these waves are maintaining a constant phase relationship. Coherence time is the time over which the waves are maintaining the phase relation. Okay, so everything about coherence is depending on the phase relation. If two waves are maintaining a constant phase relationship at a particular time and a certain time later, it is said to be coherent. And there are two types of coherence. One is temporal coherence and the other one is spatial coherence. In the case of a temporal coherence, we are measuring the coherence along the propagation direction. In the case of spatial coherence, we are measuring the coherence perpendicular to the direction of propagation. Okay, and there are two parameters. One is coherence length, and the other one is coherence time. Coherence length is the average length at which the waves are maintaining a constant phase relationship. The equation is given by h is equal to lambda square divided by d lambda. That is the square of wavelength divided by change in the wavelength. And the coherence time is the time over which the phase relationship is maintained. Tc is equal to, that is the coherence time is equal to Lc divided by C. Lc is the coherence length and C is the velocity of the light. Okay, and this the coherence is very important because we are going to discuss interference. Okay, this chapter is interference. So without coherence, interference is not possible. Okay, so coherence is very important, and this can be a short answer question or a 3 mark or 4 mark question. Understanding about the coherence is very important. One is along the direction of propagation, the other one is perpendicular to the direction of propagation. And the important parameter is the phase difference. There is a constant phase relationship, then it is said to be coherent. I hope you understand the topic. If you have any doubt, you can ask in the live class.